perpendicular bisector theorem says this: if a point is on the perpendicular bisector of a segment. Well, first we have to start with a perpendicular bisector. So we know that these two segments have to be perpendicular, and they have to be a bisector. So this segment and this segment are going to be congruent. We're going to have a midpoint. So by the definition of perpendicular bisector, we know these two pieces of information are true. We know that we have perpendicular segments and the segment is bisected. The second part of the theorem says then that point is equidistant from the endpoints of the segment. So if we have a point up here on the perpendicular bisector, it is equidistant to either endpoint. Equidistant means congruent. So by the perpendicular bisector theorem, we know this is true. And it's true for any point on the perpendicular bisector. If I pick this point right here, it's on the perpendicular bisector, it's going to be equidistant from either endpoint of the segment. The converse of the perpendicular bisector theorem says if a point is equidistant, so if I start with a point being equidistant from two endpoints, then that point is on the perpendicular bisector. So if we know this is true, then we can conclude that the segments are perpendicular and they're being bisected. The angle bisector theorem. If a point is on the bisector of an angle, well, if we have the bisector of an angle, we know by definition that these two angles are congruent. So that is one piece of information that we know is true. Then it is equidistant from the two sides of the angle. Well, this part gets a little tricky. If we start with a point on the angle bisector, we have to figure out how to measure distance from a point to a line, from a point to a side of the angle. So if I start with a line, and I call that line L, and I start with a point W, to find the distance from W to this line L, I need to find the shortest distance. To find that shortest distance, I'm going to create a perpendicular line segment. I don't want to measure the distance from here or to here. I want to go quickly there as short as possible. So if I want to measure the distance from this point to this line segment, I'm going to need to create a perpendicular line, and the perpendicular line has to be perpendicular to the side of the angle. And I have to do the same thing here to create a right angle here. So my perpendicular segments are from the side to that point, from the side to that point. So it's the angle bisector theorem that tells me this is true. I have a point and it is equidistant from either side. And it's any point. So if I have a point here, that distance to either side will be equal. The converse of the angle bisector gives me a way to prove that I have a perpendicular bisector. So if I have a point that is equidistant from either side of an angle, then I can conclude that I have the angle bisector. Let's look at a couple of examples that apply these two theorems. In example 1, we know that AD bisects angle BAC. So we have an angle bisector. So by the definition of an angle bisector, we know that these two angles will be congruent. And we have a point that is equidistant from either side of this angle by the angle bisector theorem. Well, if these two line segments are equal, I can say that 3x minus 4 equals 2x. And I can solve for x. So x equals 4. And if I plug this 4 back in, this length is going to be 2 times 4. It's going to be 8 long. And if I plug x back in here, I have 3 4s, which is 12. 12 minus 4 gives me 8. When I plug that x back in, both of these segments are the same. The second example. Line PO is the perpendicular bisector of segment AB. So I know some things are true in this picture. By the definition of a perpendicular bisector, I know that I have perpendicular segments. I also know by definition that AB is being bisected. Well, since these two are the same length, I can set up my first equation. This length, x, has to equal this length, 10. So x has to equal 10. There. I've solved for x. But I have some other things that I know are true. P and M are both on PO. So by the perpendicular bisector theorem, I know that this segment is going to be congruent to this segment. And I also know that this segment is going to be congruent to this segment. So there's my two other equations. 2z has to equal z plus 11. Solve for z. I get z equals 11. I also know that y plus 3 has to equal 14. Solve for y. I get y equals 11. But that looks kind of weird. How can y and z be both 11 if this length is much longer than this length? Well, if I look back at the problem a little bit, z is not this entire length. This entire length is 2 z's. So this entire length is actually 22. It's actually 11 plus 11, which is 22. Now if I look at this length, it's not 11, it's 11 plus 3, so it's actually 14 long, which makes sense because this is also 14. The last thing that I know is true. If I look at point K is equidistant from either endpoint A and B. That means that K is on the perpendicular bisector by the perpendicular bisector converse. If I extended PO all the way down to K, K would be on the perpendicular bisector.